Watching Formula One cars at a racecourse is a surreal experience. The fastest man-made beasts can clock up to 360 kilometers per hour or 223.6 miles per hour, which is simply insane, isn't it? F1 cars can also go from 0 to 60 miles per hour in just 2.6 seconds, which gives a kick like none other to adrenaline junkies. These cars are running engineering marvel, which has a very enthusiastic fan base as well. Every season, fans around the world flock to competitions to watch their favorite drivers and cars have a go at each other. But have you ever wondered, what is it that sets the F1 apart from other cars? How does it achieve such high speeds and acceleration? And despite the blistering speed, how can it maintain the insane road grip that it is famous for? The science behind F1 cars is complex, but we will try to break it down for our viewers. Basic physics principles and Formula One cars. Formula One cars have to be as fast and as safe as possible. It should also produce minimal drag and enough downforce to keep the car grounded. All of it is achieved by adhering to the basic principles of motion that were described by Newton. The first law of Newton states, an object will continue its motion in a straight line at a constant speed unless acted upon by an external force. The external force in the real world is friction, which is provided by gravity and the flow of air. So, the design must work around these factors to maintain a constant high speed in F1 cars. The second law of Newton describes, when a force is applied on an object, the change in motion is proportional to the force divided by the mass of that object. It essentially means that when a force, which would come from the engine in this case, is applied to the car, the lighter car would move faster than the heavier one. Hence, Formula One cars are quite lightweight and weigh just about 800 kilograms on average. To put things in perspective, an average sedan weighs around 1,270 kilograms. The third law of Newton concerns the braking system of the F1 car. It states, when a force is applied on an object, it matches the same force but in an opposite direction. Thus, when brakes are applied on the F1, it causes the tires to push at the ground, and the ground matches that force in the opposite direction. It creates friction between the tires and the ground, which ultimately leads to the stopping of an F1 car. Advanced science in F1 car. An F1 car is made up of almost 14,500 individual components, and each of them is tailored designed as per the requirement of a driver. These are designed with computer-aided design, also known as CAD, and built by CAM or computer-aided manufacturer. The point is, F1 cars are complex machines, and while the information discussed earlier is correct, it is superficial. When a car moves at a speed as fast as F1, it is subjected to several physics laws, and it must work around them to achieve top speed and a solid safety profile. Aerodynamics. Aerodynamics is the interaction of an F1 car with the air around it. Optimization of aerodynamics has unparalleled importance because it can be a make or break for the vehicle. While different companies use varying sets of components to make their vehicle more optimized, the basic principle remains the same. The front wing of the F1 car is curved upwards, which compels the air to create two pressure areas. Higher pressure region forms above the wing, whereas the lower pressure is created under it. Naturally, the higher pressure on the top pushes the vehicle downwards, which creates a suction force called downforce. It is because of this force that despite the fast speed, the car maintains close contact with the track. However, the downforce is also responsible for producing a drag that slows down the car. It is exactly why in a straight-line race, the trailing driver has a better chance of winning than the one in front. The front car interferes with the aerodynamics of the trailing car, which reduces the downforce of the latter. Hence, the trailing car experiences less drag and has a better chance of overtaking the front one with a tactic called slipstream. The leading driver can prevent the trailing car from getting this advantage by weaving the car, which makes it difficult to position the trailing car in a split stream. Since the wing does not cover the entirety of the vehicle, the two pressure regions meet immediately next to where the wing ends. The crashing of air with different pressures produces a vortex at the outer sides of the wing, which creates drag and slows the car down. To minimize the formation of a vortex, F1 features a wing tip on both sides to de-intensify the drag. Vortices are also produced in the center of the wing, which is pointed and curved in. But because of the pointed end, these vortices are directed directly beneath the vehicle and seal the clean air. The clean air works with the aerodynamics of the vehicle and makes it more efficient. It is in contrast to dirty air, which does work with the aerodynamics of the vehicle and is unpredictable. The dirty air is produced because F1 cars do not have fenders, and open spinning wheels are a major source of it. To clean the dirty air, F1 cars are equipped with barge boards, which are installed immediately next to the wheels. It not just cleans the air, but also directs the dirty air away from the body of the vehicle. Naturally, F1 cars produce a lot of heat, which makes the vehicle break down if not addressed properly. The aerodynamics of the vehicles direct that clean air into side pods, which pass the airstream inside the car before letting it out from the rear. Furthermore, the overall shape of the F1 cars is designed to smoothly guide the airstream above it even in extreme conditions. It ensures that drivers get predictable handling even at higher speeds. The changes in aerodynamic design in 2022. As discussed earlier, the dirty air produced by the leading car can help the trailing car in a straight line, but it can also be a problem for the trailing driver during cornering. It is because the aerodynamics of the previous car is disturbed by the dirty air coming from the leading car. Hence, the trailing car is not able to generate the downforce that is required while cornering. Essentially, it takes longer for the trailing vehicle at the corners, which can result in the loss of a race. Regulatory bodies of the F1 have compelled the companies to make changes to the aerodynamic designs of the cars. The new aerodynamics would allow cars to race at close range without interfering with the aerodynamics of each other's cars. Thus, the front wing and nose concept of the F1 vehicle has to be revamped completely. The new design features rolled tips, which are designed to push the air higher at the back of the car. Hence, the trailing drivers would not have to experience dirty air, consequently allowing closer chases at corners. A 3D floor design has also been introduced, which produces a more efficient downforce without interfering with the airflow behind the car. The changes in the design have produced a significant impact on the overall aerodynamics of the vehicles. To put things in perspective, the previous models of F1 cars experienced an estimated loss of 35% of downforce at a 20 meters distance and 46% at a 10 meters distance. But the recent changes have cut down these figures significantly. The cars now experience just 4% downforce loss at 20 meters at 18% at 10 meters. All of it indicates that we would witness some very close competition and interesting overtaking at the corners in the new season. We hope this video was informative and fun. Stay connected with us to learn more about Formula One cars and everything else associated with them. We will see you at the next one.